All right, 6.3, interpreting the rate of change of exponential models. Okay. This is mostly word problems, and to be honest, it all looks a lot harder than it really is. It's actually pretty dang simple. Before we get into answering some of these word problems, though, we have to know the basic layout of an exponential problem or an exponential function. So I put all the parts here so you could see it. So if we had some function f of t now, I'm using t instead of x because usually these types of functions are going to be with respect to time. So t represents time in some units like days or hours. And that t is going to be in the exponent. And then you have p. This p stands for principal amount or starting amount. That's how much you had to begin with. Whatever number is right there. The r, this is a rate of change. It's usually entered as a decimal, but it's often discussed in word problems as some type of percentage. So the way this works is if it's a positive percentage, like say 10%, you'd do 1 plus 0.10, so that'd be like 1.10 in there. And if it's negative, then it would actually be 1 minus 0.10, so that would actually be a 0.9 in there. So just know that it's all either going to be adding a decimal to 1 or subtracting a decimal from 1. And then finally, when you plug all this in, the thing that you get out is, and this F could be any letter. It doesn't have to be F. It could be V, as you see in this problem, or P, or Q, or any. It doesn't really matter. But it could be any letter, and it represents the end result based on a given amount of time. So you should be able to plug in a number for, say this is talking about years. You should plug in like 3 years, and then you'll get an answer of, how much growth or decay has happened after those 3 years. Okay. So we're going to refer back to this chart whenever we need it. Let's take a look at this first problem. So it says Mr. Price uploaded a funny video on his website, which rapidly gains views over time. The relationship between the elapsed time t in days since he uploaded the video and the total number of views, v of t, so v of t is the total number of views, and t here is the number of days since he uploaded it, is modeled by this function. So here we have this function. And we have 100. And remember that 100 is right there at the beginning. It's where the p is. It's the principal amount or the starting amount. That's important. And this says 1.65. So that means that we started, 1 plus our r here is actually 0.65. So how many views does this video have on the first day? Well, that's just this number right here. It's the number that we started with. So that should be easy. That's just 100 views. Remember, because that number out in front is our principal amount or starting amount. So that's how much we had on the first day. Now, actually, a better way of phrasing that question would be like at the beginning of the first day, because actually, if we plug in a 1 there, we'll get something other than 100. So maybe I should have said how many views did his video have on the beginning. I know my handwriting sucks, but that should say beginning, because technically it's at the beginning of the day that he starts with 100, and then throughout that day it grows. All right, are the views being added to or subtracted from each day? Well, it says that it's rapidly gaining views, so we could say it's being added to, because it's growing. It's not getting smaller. Remember, if it was getting smaller, this number here would be less than 1, because the r value would be negative, and we would be doing 1 minus some decimal instead of 1 plus a decimal like we did here. Okay, next it says, what is the percent at which these views are changing each day? So that right there might be the hardest question in these types of questions, and it's really not that hard if you think about it, because we said right here, this is a rate of change. It's entered as a decimal, but it's often discussed in word problems as a percentage. So this is what we're looking for. What percent is it growing? Well, it's just that 0.65. If I was to write that as a percent, right, 0.65 as a percent is 65%. So it's growing by 65% each day. So every day we get 65% more views. All right, so then this thing says, what if the function was, so what if we had a different function? What if it was v of t equals 500, 1.10 to the t? I want you to think about this on your own and see if you could just answer this. What would change? What would be different about this? Think about that. Maybe answer that question on your own. Pause the video, think about it, and then come back when you're ready to check and see what would actually be different. Well, the first thing is, up here, that would be 500 instead, right? We'd have 500 views at the beginning of the first day instead. And the second is right here, this would not be 65%. Instead, it would be growing by 10%. So you could write that in a complete sentence. It's kind of hard to do it with my little stylus here, but basically we could say something along the lines of, you know, it would start with 500 views instead of 100, and it would be growing by 10% instead of 65%. And that's all that would be different, because those are the only things that really changed there. The overall layout didn't change. It's still being added to. It's still growing. It's just growing by a different rate, and it started with a different amount. All right. Let's go on to the next problem. Okay. This says Miss Rausch began studying a sample of the chemical element Einsteinium, number 253. And this chemical element naturally loses its mass over time. The relationship between the elapsed time t in days since she started studying the sample and the total mass remaining in the sample m of t, sorry, there's an extra comma there, m of t is in micrograms, is modeled by the following function. Okay, so we have this function telling us about how this decay is happening. I want you to notice this 0.93 tells us that this, remember that this is typically like a 1 plus r, but in this situation r is negative. So we could say in this situation it's actually going to be like 1 minus r, right? Because it's going down. You can still think of it as 1 plus a negative r is kind of how I think about it. Okay, so we got a couple questions here. It says, what was the mass when Miss Rausch started studying the sample? We should be able to tell that pretty easily. Is the mass being added to or subtracted from? That also we should be able to tell really quickly whether it's growing or decaying. We could see that in the word problem. We can also see that in the equation. And then it says, what is the percent at which the mass is changing each day? Now that one might take a little bit of thinking, but I think you can figure that one out. So I want you to try and answer all three of these on your own. Pause the video, give it a shot, and then come back when you're ready to check your work. Okay, so the amount or the mass when she first started studying the sample, that should be easy. Remember, that's just the number out in front that we started with, so that's 159, and they said that's micrograms. Is the mass being added to or subtracted from? Well, we know it's being subtracted from. We know it's shrinking because they said it loses its mass over time, so that's pretty easy. Also, remember this number is less than 1, so that means it's shrinking. If this number is less than 1, it's shrinking. If it's greater than 1, like in the problem before, it's growing. Pretty simple. So we know it's shrinking. What is the percent at which the mass is changing each day? This takes a little bit of thinking, but remember, this number in here is 1 plus your r. We really want to know that r. Well, if 1 plus my r equals 0.93, I could just solve for r, subtract 1, or you could think about it. What would you have to add to 1 to get to 0.93? And you'd have to add a negative 0.07, which is like saying a negative 7%. So what is the percent? It's negative 7%. Pretty easy. Pretty easy question. All right. So even though it's a word problem, nothing to be scared about. It's all pretty straightforward. Okay, let's go to the next page, though. Okay, we got a couple more questions here. And these ones get a little bit interesting. Okay. Example 2 says, after a special medicine is introduced into a petri dish containing a bacterial culture, the number of bacteria remaining in the dish decreases rapidly. The relationship between the elapsed time t in seconds now, so t is in seconds, and the number of bacteria in the petri dish is modeled by the following function. So this one looks a little bit different. We can still see the starting amount is 5,000. 3/7 is less than 1, so we know it's shrinking, which makes sense because they said containing bacteria, the number of bacteria remaining in the dish decreases rapidly. So it makes sense that that's less than 1. And then we have this t over 6. What's that all about? Well, let's think about this. It says the bacterial culture loses 4/7 of its size every blank seconds. Why 4/7? Well, remember, what did we say is really going inside these parentheses? We said it's really, I'll do it over here. We said that's really 1 plus r, right? Well, if 1 plus r equals 3/7 right now, we could figure out what r is, and we could probably figure out where that 4/7 came from. In fact, you might even see it without even really doing the math, because if I did 1 plus a negative 4/7, that would give me to 3/7. And we could kind of just do the algebra here and see. If you subtract 1, you end up with r equals 3/7 minus 1, which is really like saying 7/7, which is negative 4/7. So that's important to see where that's coming from. That's because 3/7 is 4/7 less than 1. So that's where that's coming from. Okay, so that's why it's losing 4/7. Now, how often is it losing 4/7? Well, here's the deal. It's going to lose 4/7 every time the exponent here equals 1. That's it. It's going to go down at that rate every time this equals 1. So what makes this equal 1? Well, I mean, this is a pretty simple algebra problem if you just want to set t over 6 equal to 1. But think about it. What over 6 equals 1? It has to be 6. I mean, you could do the algebra if you want. You could have t over 6 equals 1 and multiply both sides by 6, and you could see, but it's just t equals 6. It's just the number that makes the exponent equal 1. So the bacterial culture loses 4/7 of its size every 6 seconds. That's it. Pretty easy. All right. It looks like a hard problem, right? But it's actually really simple. We see why they got that 4/7, because they're just doing 1 plus a negative 4/7. And we can see why it's 6/7, because it's when this has to equal 1, when the exponent equals 1. So the next problem you'll probably be able to do just without even reading it. But it says, Mr. Busher started studying how the number of branches on his tree grows over time. He's got lots of trees in his yard, in case you don't know. The relationship between the elapsed time t in years since he started studying the tree and the number of its branches, n of t, so n of t represents the number of branches, and t represents the time in years, is modeled by the following function. So we can tell that it started with 19 branches, and then it says times by 4 to the t over 12. Okay, so the number of branches quadruples. Well, quadruples means multiply by 4, so that's where that 4 came in, every blank years. So I'm going to let you look at this and see if you could figure out how long it takes for it to quadruple. Go ahead, pause the video if you need to, and then check back when you're ready. Okay, well, once again, hopefully you saw. Remember, it's just when this exponent, sorry, I wanted to circle the whole thing. It's when this exponent equals 1. So t over 12 has to equal 1. Well, that's pretty easy, right? It's going to be 12. I can do the algebra, multiply both sides by 12. But it's just t equals 12. It's going to take 12 years for it to quadruple. That's what that exponential equation means. So again, we get this long word problem. We think it looks really hard, but really all we got to do is see, well, what would I have to plug in for t to make this exponent 1? That's all they're really asking. All right, that's it for 6.3. I'll see you guys on the next video.